This is the continuation of the uh, video number 1 on transformation of graphs, and this is video number 2 of part 2 of transformation of graphs. Okay, so as I mentioned in my earlier session that transformation means what, and with regard to that we had already started with one of the transformation, that is from f of x to f of uh, x plus k, where k is a positive integer. And I had given you an example of y is equal to x square as a parent. You can see over here, y is equal to x square as a parent function, which you can see over here. And y is equal to x plus 2 the whole square. This is nothing but a transformation function in which you have added 2 to x, or you can say you have added 2 to the domain of this function x square. So it makes it y is equal to x plus 2 the whole square. And you saw that the graph was shifted to the left. So whenever you add, the graph gets shifted to the left. That was in the case of y is equal to x square graph. Similarly, you saw that the 0, 0 point on the parent graph was shifted to -2, 0. So here you have to do what is, from the x coordinate you have to subtract that amount k. Okay, if the transformation is x plus k, right? Same thing we saw in the case of root x and root x plus 1. Okay, so now we are going to do one thing today. We are going to see these two things happening exactly on the this thing also. Okay, on the GDC. Okay, so I'll take you to the GDC and I'll show you there how the same thing can be seen happening over there. Okay, so for that I'll be taking you to my document camera, and you can see there in my document camera you can already see that GDC. I'll slightly magnify it. Right now in GDC I'm going to go to the graph section. So first new, and then yeah, can you see? Now I'll go to add graphs, and you can see I'm on the graphs page, and I'm going to plot both y equal to x square and y equal to x plus 2 the whole square on the same axis. Okay, so first let me do y is equal to x square, so that will be x squared. Okay, and I will graph it, so you can see that the graph is ready for that. Okay, so this is the graph of y is equal to x square, and on the same graph I'll be making a graph of y is equal to x plus 2 the whole square. Okay, so open parenthesis x plus 2, so plus 2 will be over here, plus 2 close parenthesis raised to 2. Okay, now this is my second graph, which will be overlapping on this only, right? So x plus 2 the whole square ka graph, if I'm plotting, see what will happen. This particular graph y is equal to x square will be shifting to the left. Okay, and here you can see that happening. Yeah, did you see that? So the blue color graph was the original y is equal to x square graph, and y is equal to x plus 2 the whole square is a transform graph, and it has shifted to the left. Is that clear? Fine. Now let us try the same thing for root x as well. Okay. So for root x, we will do what? We will again go and let me do one thing. First, cancel this. Right. Now I don't want to save this. Yeah. Okay. Now I'll again do the same thing for uh, this thing, okay, root x. So I'll go to add graphs, select it. Now I will do root x, square root of x, and square root of x graph should be over here. Okay. Mm, yeah. So it will be square root of x. Okay. Now this is the graph of square root of x. Now same thing I have shown you on my Wacom tablet as well. Okay. This is square root of x. Now this I will be saving and I'll be doing again square root of x plus 1. Okay. Square root of x plus 1, right? Plus 1, right? Now this graph when I plot, this graph will, transform in such a way that it will shift to the left by 1 unit because I have added 1 to x. Okay. So let us see that happening. Yeah. Yeah. Can you see that the graph, the red color graph has shifted by 1 unit to the left. Okay. Now let me do one more thing. If I want to add 2, if I add 2 to this x, okay, what will happen? So let us see that also. The square root of x plus a 2 I am doing this time. Okay. Square root of x plus a 2. Now if I do this, so this graph will be shifting by 2 units to the left. And see that happening over here. Yeah. Can you see that? So the third graph that I've plotted just now, okay, has can you see that? Okay. It has gone 2 units to the left, right? So generally speaking, what happens is the graph shifts to the left when you add something to the x in the parent function. Is that clear? Okay. So with that, I'll end up this and I'll take you again to the Wacom tablet to go with the further things, right? Okay. So we saw x square and x plus 2 the whole square graph over here. And we saw this also happening, root x and root x plus 1 graph. Okay, shifting 1 to the left. And in this case, the coordinate from the x coordinate, you'll have to subtract 1 in the case of this root x plus 1 graph, right? The third example is modulus of x graph and modulus of x plus 2. Again, here modulus of x graph you can see over here. Its vertex is passing through 0, comma 0. Okay, so that point you can take for reference. And in modulus of x plus 2, this graph has shifted to the left by 2 units. So this point 0, 0 has automatically come to minus 2, 0. So the coordinate that I've chosen is 0, 0 from the parent function, and from the x coordinate that is 0 of the parent function, I have subtracted 2 to make it minus 2, and the y coordinate I have kept is as it is, okay, 0, 0. So this was the third example, and one more example cos x, that also we have discussed already, 0, 1 and minus 2, 1. Okay. Now let us go for the second type of transformation, which is y is equal to f of x. Okay. This is that second kind of transformation in which y is equal to f of x will be okay. Yeah. So y is equal to f of x to y is equal to f of x minus a k. Okay. Now this is very much similar to y is equal to f of x plus k transformation. Now in x plus k transformation, you saw that the graph is shifting to the left. Here you will have to do what? You will see that the graph is shifting to the right by that same amount k. So suppose you have a graph of y is equal to x square. You can see a this blue color graph is of no, sorry, the white color graph is of I will write that for you over here. So you can see very clearly that this one, this inside one, this is the graph of y is equal to x square. Okay. And this blue one is the graph for y is equal to x minus 2 the whole square. Okay. So when you subtract 2 from x, okay, then the transformation will be such that the graph, the original parent graph, will shift to the right. By how much unit? By 2 units. So that is why this point this reference point 0 0 will shift to 2 comma 0. Okay, so here you have to remember, in general, suppose there is a this type of transformation taking place. Okay, so suppose you have a x and a y in general, and this transformation is say x minus a k. Then what will happen? You will have to add k to x, and this y you will have to keep it as it is. This is the general way of understanding. So if you take this 0 0 from the parent, okay, then from 0 you'll have to subtract, you'll have to add 2, okay, because this is x minus k transformation that is taking place, right? So for x minus k, you'll have to add 2. So x 0 plus 2 will be 2. And the y coordinate, you have to keep it as invariant. Okay, so this y will be invariant. Invariant means it is not changing. It is remaining as it is, invariant. Okay. Now same you can see happening over here in the case of root x and root of x minus 1. Now because 1 is subtracted from the x, you will see that the graph of root x, that is this one, is shifting by 1 unit to the right. Okay, so here the shifting is to the right. So you can write here that graph is shifting, graph is horizontally shifting to the right. Okay, when the transformation is from f of x to f of x minus a k. Okay, so this is what is known as horizontal shift to the right and to the left. Okay, there's one more example, modulus of x. You can see this white color graph is for modulus of x, and this blue color graph is for modulus of x minus a 2. So when you do x minus a 2, okay, then the graph will be shifted again, horizontal shift of 2 units to the right. Okay. It will be right because this time it is minus, right? And okay. And here you can see that in general, if you have a x comma y, I mean xy as a coordinate, then it will be x plus 2, and this will remain invariant. Okay, the same thing you can see happening over here. Same way, the last example is cos x to cos x minus 2. Now you can see this white color graph is of cos x, and this blue color graph is of cos x minus 2. Okay, now this is also a example of horizontal shift to the right, horizontal shift to right. Okay, now when it is minus 2, the shift will be in the opposite direction, that is right. Okay, so here again, in general, if you have a xy coordinate on the parent function like cos x, so in the transform function you will have x plus 2 and y, right? And at that point you can take as on the x-axis, let me take this as that point. You see this point is 0 comma 1. Okay, and this point has shifted to the right, that is over here. Okay, in the transform function, and now the coordinate will change to 0 plus 2 is 2 comma uh, sorry 0 plus 2 is 2 and comma 1. Okay, 1. So can you see this coordinate is 2 comma 1, right? Okay, so summary of this transformation that we have studied so far is this. Suppose you have a parent function as y is equal to f of x, and it is getting transformed to y is equal to f of x plus k, where k is a positive number. Then the graph of the parent body will shift to the left by k units without any change in the shape and size of any other part, any other part of the parent function. Okay, parent function. And when f of x, y is equal to f of x is transformed to y is equal to f of x minus a k, where k is a positive number, then the graph shifts to the right by k units, and the graph shifts to the right by k units, and the other aspects remain unchanged. Remain unchanged. Okay, fine. Now this can be understood in a different way also. I've written a big or for that. Okay, suppose you have a point, okay, as x and y, okay, which can be written in the form of a column vector xy. This is x coordinate and this is the y coordinate. Now this is a point on a function f of x, and this is a point on a function f of x plus h. So whenever there's plus h, from x coordinate you have plus k. Okay, from x you have to subtract k, and the y coordinate you have to keep as it is, invariant. Okay, and second is this. Suppose you have from f of x to, yeah, it was f of x to x plus k, and suppose you have f of x to x minus k transformation, then from x you have to add. Okay, so it will be x plus k, and the y will be remaining same. Is that clear? So that was the first transformation, and now I'll be taking you to the second kind of transformation, and that is something which is in general known as dilation. But these words, they are very confusing. Dilation and horizontal shift, vertical shift, so we have completed. This dilation actually comprises of two things, that is either a horizontal compression or a horizontal stretch. Same way there can be dilation along the y-axis, which can be again comprised of either vertical compression or a vertical stretch. So I'll write that for you for your reference. Whenever you say dilation, dilation is a word which has two meanings, either compression or stretch. Okay, and again this dilation can be along either the horizontal direction or a vertical direction. So dilation can be horizontal or vertical, and again it can be horizontal compression HC or horizontal stretch HS. If it is vertical, again it can be vertical stretch, or it can be vertical compression. So these are the another four types of uh, transformation that we are going to deal with. Okay, something called horizontal stretch, horizontal compression, vertical stretch, and vertical compression. Remember, we have already completed two types of transformation, T1 and T2, T1 and T2, which was nothing but horizontal shift to the right and horizontal shift to the left. These were the two transformations that we have already studied, we are done with, and now we are going to deal with this four more types of transformation. Total it will be six. Okay, after that you have two more transformations, that is the reflection in the x-axis and the reflection in the y-axis. Okay, so total there will be 8 transformation that you have to study. Okay, so coming to this second part, in this you have this second type of transformation. In general it is known as dilation. Okay, now let us try to understand this. Suppose you have a parent function y is equal to f of x, and if you are multiplying the x, that is the domain, by some constant, by some number k, which has to be positive. Okay, then what will happen? Okay, so when you multiply the domain, or you multiply inside the function, which is x, okay, by some positive integer, what will happen to the parent function that we are going to study? Okay, so let me tell you by giving you one example. Suppose you take y is equal to x square as your parent function. So can you see your parent function is this one, the white one? Okay, this is y equal to x square, the parent function. Now suppose in the parent function inside the bracket, that x you are multiplying by this number 2. So your k is 2, which is a positive number. So when you do that, what will happen? Okay, so remember that whenever you do this type of transformation, that is when you multiply the x by a positive k, okay, what will happen? This particular parent function will be compressed, okay, and it will move closer to the y-axis, and this particular phenomenon that is happening is known as horizontal compression, because this parent function will be compressed, it will be pushed in the inner direction, okay, and this compression is taking place in the horizontal direction, and that is why it is known as horizontal compression. Is that understood? So I think you must have understood the meaning of this horizontal compression. So the graph will be getting compressed, okay, in the horizontal direction. Okay, so from left to right, or you can say from left to right. Horizontal compression is nothing but from left to right. From left to right, the graph will get compressed. Okay, and the other things are going to remain same, that is there will not be having any change in the vertical direction, right? So that is this particular transformation. So in this example you can see very clearly that this white color graph, which is of y is equal to x square, and this blue color graph, which is representing y is equal to 2x the whole square. Now these two graphs, you can see that the second graph, the blue color graph, has been compressed, and it has been compressed in the horizontal direction. Okay, fine. So that is how we have to understand this particular transformation. Now let us try to understand what is happening to the coordinates. Okay, so let us try to take one coordinate, say 1 comma 1 from f of x. So this is a coordinate, this is a point 1 comma 1 from y is equal to f of x, okay, which is nothing but x square, right? And after transformation, what is the transformation? Y is equal to f of 2x the whole square, okay, 2x, right? So y is equal to 2x the whole square. This is the new function or the transform function. Now here on the blue graph, if you want to keep the y same, okay, that is 1 and 1, right? This is on f of x, I have taken the point 1 comma 1, okay. So on the y-axis also I will take the y, on the transform graph also I'll take the y coordinate 1 only. So for 1, what will be my x value? So you can see that for 1, my x value is 1 divided by 2, okay, that is half. So my x coordinate in the transform graph is 1 by 2. So what is happening is, if you multiply this x by k in the transformation or in the transform graph or in the new graph, that x should be divided by that quantity k. So that is why I have divided 1 by 2 over here. Can you see that? Let us take one more example. Suppose you take 2 comma 4 on the parent function. Parent function is x square. So I have taken that 2 comma 4 where, okay, it's over here. Can you see this? So this 2 comma 4 is a point on the parent function, and on the this thing, that is the transform function, that is blue one, for same value of y4, that is this, the x will be how much, that I will see. So x will be 1. So the point will be 1 comma 4 on the transform graph. So this is x plus 2 the whole square ka graph. On this I am getting 1. How I got this 1? This 2 I divided by 2, and that is how I got 1. Why I divided by 2? Because in the function, it was the domain was multiplied by 2. So you'll have to divide this x coordinate by 2. Okay. And this is how you get a horizontal compression. So these are the things you have to keep in your mind. What is happening to the points, okay, when this transformation is taking place, and what is happening to the shape of the graph, that you have to remember very well. Okay. So in this case, you will see there's horizontal compression taking place, and coordinate may the changes is from the parent to the transform this thing, the x coordinate, when you multiply by k in the transform function, x will have to divide by that k, and y will be remaining as it is. It will be invariant. Now let us try to understand this same thing by the second graph. Okay, that is root x graph. So in root x and y of y is equal to root of 2x. Again here in this transformation, I am multiplying this x by 2. Okay. So this will also result in horizontal compression, because in general, when f of x is being transformed to f of kx, okay, where k is positive, okay, the transformation will be such that the x will be divided by k. So the coordinate, suppose this is xy, okay, after the transformation, this x will be divided by 2 and the y coordinate will be remaining as it is, right? So this is what you can see happening over here. 1 is getting divided by 2, so 1 by 2 I am getting here, and the y coordinate is remaining same. Okay, so this was an example of root x and root of 2x. Same way you can under the same lines, on the same lines, you know, you can understand root modulus of x and modulus of 2x. In modulus of 2x, you can see again that x has been multiplied by 2, or it can be any other number, not only 2, it can be 3, it can be 4, but it should be positive number, right? So by that amount, you will have to divide the x coordinate, and you will see that there is horizontal compression taking place. What I mean by horizontal compression, this parent graph will be pushing itself in the inward direction and in the horizontal direction. Okay, so this is all about horizontal compression, and this is happening when you multiply the x by some constant k, which has to be positive. Okay, so horizontal compression, I've given you so many examples. There's one more example, cos x to cos 2x. Again here you can see that white graph is for cos x and the blue graph is for cos of 2x. And you can see, if you carefully see this coordinate, okay, the 1.5 comma 0 on the y is getting converted to 0.75 comma 0. So 1.5 is getting divided by 2 to get this 0.75, right? So if you see this all carefully, you will definitely get an idea of what is happening when the x is getting multiplied by some constant k. So this transformation was the third type of transformation that we can consider. So you can say that in summary, you can say that this y is equal to f of x, the parent function, when it gets transformed to y is equal to f of kx. Okay, what is going to happen? Any coordinate xy taken on the parent function will get transformed into x upon k and y. So the x coordinate will get divided by k, because here it was multiplied by k. So the coordinate x coordinate will get divided by k, and the y coordinate is going to remain the same. And the fourth transformation is when f of x, that is the parent function, is getting converted to f of x upon k. Now here you can see that this positive k, you are dividing x by that positive k. So when you divide the x by positive k, you will get a new type of transformation, which will be called as horizontal stretch. So far it was horizontal uh, compression. Now this compression can also be written as, if you want, you can consider it as shrink also. In many books, you know, they prefer this word shrink. instead of compression, but both have literally the same meaning. So whether you call it horizontal compression or horizontal shrink, it doesn't make any difference. So here you will be finding now horizontal stretch. Now what I mean by horizontal stretch is the graph, the parent graph will be moving outward. It will be stretched in the outward direction, okay, in the horizontal direction, right? So it will be pulled from right to left. Okay, so you can use this word, pulled from left and right. Okay, so the parent function will be pulled from left and right, and it will get expanded in the horizontal direction, right? So there are so many words that can be used, but we will stick to this horizontal stretch over here. This also means horizontal expansion, okay, which is just opposite of compression, right? So let us see the graph of y is equal to x square. So this is your y is equal to x square graph. Can you see this, right? This is your parent function, and transformation is happening by y is equal to x upon 2 the whole square. So x you are dividing by 2. So you get this as a resultant function, okay? X upon 2 the whole square, right? Now, what is happening to the graph? The graph in this case is getting stretched in the horizontal direction. So, white graph is getting stretched in the horizontal direction, and it is coming to the position of this blue graph, right? And what is happening to the coordinate in terms of coordinate? Suppose you take a coordinate, say 1 comma 1 on the parent function, that is y is equal to x square. Then what will happen, because it is x upon 2, your x coordinate will get multiplied by 2. So 1 will be getting multiplied by 2. So you get 2 over here, and the y coordinate will be remaining same. So 1 and 1. So on this x upon 2 the whole square graph, you will get the corresponding point as 2 comma 1. So for 1 comma 1, the shift is 2 comma 1. So you can say that this point 1 comma 1 has shifted to point 2 comma 1. Okay, so this way also you can say. So this is happening when the horizontal stretch takes place. This is the, remember, this is the fourth type of transformer that we are dealing with. Let us take some more examples. Now, this is an example of sin x graph, which is a parent graph, and this is sin x by 2, which is again a transform graph. And you can see that x is getting divided by 2. So when x is getting divided by 2, it is understood that it has to be a horizontal stretch. Can you see this white graph? This white graph is getting stretched in the horizontal direction. Okay, so it is getting stretched and coming to this position, right? It is forming this blue color graph, right? And this is getting stretched and it is forming this blue color graph, right? So basically what will happen, horizontal stretch, x value will increase by the x value will increase, but the y value will remain same. Now why x value will increase? Because this is x divided by 2, so the coordinate will get multiplied. Okay, so let us try to see the coordinate. Now suppose you have this on sin x graph, you have a point pi comma 0. Now this, you know, this graph, don't get confused, this 1 2 3 4 are the real numbers, but actually the graph should be in degrees. For the trigonometric graph, it should be in degrees on the x-axis. So this is that pi by 2. I've taken in radians, pi by 2. This is pi, this is uh, this is pi, this is 3 pi by 2, and this is 2 pi. Okay, this is 3 pi by 2. Or you can say this is 90 degree, this is 180 degree, this is 270 degree, and this is 360 degree. Okay, so if you take in degree, the x-axis, if you take in degrees, you will see that for sin x graph, pi by 2 x coordinate has a value of 1 as y coordinate. So the point will be on sin x, you can take the point as pi by 2 and 1. Okay, now this particular point, after transformation, what happens to this point? So this pi by 2 now will get shifted to a new coordinate. this pi by 2 comma 1 will get shifted. Now x will be multiplied by 2. So we had divided by 2, pi by, no, it was pi, one second, this is 0, pi by 2, that is this example. So pi by 2, the corresponding value is 1. So this pi by 2, you will have to multiply by 2, okay, because the graph is sine x by 2. So when you multiply pi by 2 by 2, 2 will cut and you will get a pi, and y coordinate will remain as it is. Okay, so it will be like this. Okay. So pi by 2 comma 1 will be shifting to pi comma 1. Can you see here? Pi by 2 1 will be shifting to uh, pi by 2 1 will be shifting to pi 1. Okay, you can see here that transformation taking place, right? So such transformation where the x has been divided by some positive value k, then horizontal stretch is taking place. Okay, so the x value will be increasing because it will get multiplied. The x will get multiplied by that k factor, right? So all these were examples of uh, this four transformations that I wanted to teach you all. And now I'm going to talk something about these transformations in a general way. So if y is equal to f of x is a parent function, and if it is transformed to y is equal to f of x upon k, where k is of course a positive integer, then the graph, what will happen? It will be stretching from left to right, or you can say there will be horizontal stretch. Okay, horizontal stretch, and the x coordinate will get multiplied by k. Okay, so the coordinate may changes, you will see that the x coordinate will be getting multiplied by that k factor, y coordinate will be remaining same. So now here I have mentioned horizontal shrink and compression is equal to vertical strain. Now this is not correct. Okay, I'm sorry that I wrote this, but one thing is clear: you should not consider this as same. Okay, in fact, it is not equal to. Okay, so you don't think that horizontal stretch is same as vertical shrink or compression? No. Okay, so this is a very big blunder. So you should not think that both are same. Okay, these two are two different things. They both are not the same effect. So you cannot say that the horizontal stretch is the same effect as vertical shrink. No, it is not. Right? Now, this one more function will explain you. Modulus of x is the parent function and modulus of x upon 2 is the transform function. So you can see this white graph, the parent graph, is getting uh, stretched out in the horizontal direction, right? It's getting stretched out in the horizontal direction, outwards, right? And it is forming this blue color graph, right? And all these are the changes in the coordinates that you can see, and I've already explained you about this. So this is what happens to y is equal to x upon 2. So four transformations I have already taught you. So if you want to summarize all these four transformations, then I can tell you that y is equal to f of x. Okay, now this is the final uh, summary. From y is equal to f of x to y is equal to f of x plus k will be horizontal shift. HS means horizontal shift to the, now if it is k, I mean plus k, it will go to the opposite direction, that is left. Okay, and if it is f of x to f of x minus k, then the shift is on the it is getting subtracted, so the graph will be shifting in the horizontal direction, horizontal shift to the right. This is 1, this is 2. Then we studied this f of x to f of kx. Okay, in the case of f of x to f of kx, we saw that there is a horizontal compression, okay, of the graph, or you can say the graph is getting compressed from left and right, from both the direction. It is getting compressed. Okay, and f of x to f of x upon a k, here you will see that there is a horizontal shift taking place. Is that clear? This will be horizontal shift. So these are the four different types of transformations that you have studied so far with me. And there are, as I told you, in total there are 8. Okay, so there are 4 more to go. Let me tell you that also, which are the 4 more to go. So you have this one, f of x plus k, f of x to f of x minus k, and f of x to f of minus x, and f of x to minus f of x. So when we complete this 4 also, in total we'll be completing 4 plus 4, 8 transformations. Okay. So this remaining 4 I'll be taking some other day, some other time. So that's all for today. Goodbye. Take care, or take care all of you. Bye.